Okay, so this is the second lecture, and fortunately, all of you have successfully submitted your homework program to me. So I will check it, and you can find that actually all of you have a score of 10, although the full credit is 100. It is because this is automatically set as 100, and I think that each problem in this homework will have a weight factor of 10. So if you have 10, then it's good. But I wanted to ask you something like this. Some of you have clearly submit a report, so good to evaluate, and some of you just submit files like something like that Python like this. So if you submit just your own code, then it would be very difficult for me to evaluate it. So usually, as I told you before, I will not actually execute your code. So I will make an evaluation based upon your report. So do not submit your source code only. So please provide a sufficiently well-written report to me to help me to evaluate your report in a reasonable time scale. Okay, so are you with me? So some of you gave me the report and some of you didn't. But in this homework one, the main purpose was just to test your capability or your ability to submit homework. So all of you got 10 points. However, from the homework number 2, please submit a reasonable report on your problems. So are you all with me? Please. And some of you gave me some files like based upon MS Word, and some of you PDF, and I prefer to have a PDF file. So if you don't mind, please convert your MS Word file to a PDF file. Then that would be quite convenient for me to read your homework submissions. Okay, so that is one thing. And anyway, good job. And today is the second lecture time, and we will talk about oxidation of our silicon substrate. So let's go to the one. So usually in previous lectures, previous semesters, we have discussed only device simulation. However, in this semester, I wanted to discuss a little bit about the process simulation. So this is a quite brand new attempt for me. So let's go to the oxidation. Oxidation means that we wanted to produce a thin layer. Thin, how thin is it? It really depends on the situation, but sometimes it can be just a few nanometer thick, but in some cases 110 or 100 nanometer thick oxide layer. So silicon dioxide layer. So as I told you before, we have a silicon substrate. So typically when we say deposition, so it introduces a new layer which does not consume our silicon substrate. However, in the case of this oxidation, actually our silicon substrate is consumed and this silicon part converted into silicon dioxide layer. So silicon dioxide is so good insulator in this case. So we are using silicon dioxide almost everywhere in our fabrication process. So silicon dioxide, this oxidation is so important. So since we have already silicon atoms in our substrate, in order to make our silicon dioxide, required thing is actually oxygen atom. So if we can apply oxygen atom into the surface of a vapor, then with a sufficiently high at a time sufficiently high temperature, we will have the chemical reaction like this. So there are two representative way to make this these reactions. One is providing a water vapor. So in this case, here we have O, and this oxygen atom makes some reaction with the silicon substrate and becomes silicon dioxide layer. Of course, we have a byproduct. What is the byproduct? In this case, here we have H2, and this hydrogen vapor is generated. And in the case of the second line here, we directly supply only oxygen gas. Then this oxygen gas directly make a reaction with the silicon substrate atom, and in this case we have silicon dioxide and no byproduct is made. Okay, so in this case, in this second case, we are not related with any kind of a water molecule. So sometimes people call it as dry. No water is involved. However, if we go to the first line, something happens to my mouse. So let me just, okay, this is the time. Okay. Um, in the first line, we have water vapor. So people call it as, sorry about that, people call it as wet oxidation. Okay, so here wet is, the terminology wet is related with the existence of water vapor. So now let's go to the second line here. Amorphous silicon dioxide, when we measure its weight density, it has the values like this or like this. It depends on the ways we make this silicon dioxide. However, compared with crystalline silicon dioxide, sometimes called as quartz, it has lower weight density. So why it has lower weight density than this crystalline silicon dioxide? It is because this silicon dioxide made by this wet oxidation or dry oxidation is not crystalline. They are amorphous. So that's the reason why we cannot closely pack our atoms in a given volume. Now think about this case. If we have many books and a box, and if we just make an ordered way to place our books, then we can increase the weight density. However, in a box, let me just put my books in randomly, then what will happen? There will be many empty space inside the box, so weight density will be decreased. Quite similarly, since our silicon dioxide is actually amorphous, so weight density is somewhat lower than that of crystalline silicon dioxide. Okay, that is one thing. And this is a simple description about kinetics. So here we have silicon substrate. This is a substrate, and here we have oxidants. So here oxidants means that sometimes silicon, oh sorry, no silicon. So in this case, water vapor in wet case, or O2 molecule in the case of a dry case. So one oxidant, let's say that one oxidant in the case of wet oxidation, we need actually two oxidants to make one single silicon atom to be oxidized. Okay, so we need two oxygen atoms. However, our H2O molecule contains only one atom, so we need two oxidants in the case of wet oxidation. And in the case of dry oxidation, since we have two atoms in it, so only with one oxidant we can make this reaction, and one single silicon atom can be oxidized. So are you with me? I'm talking about this one because later we will talk about the volume density of oxidants. Mhm. So volume density of oxidants means that per unit volume, how many oxidants are there? That is the concentration of oxidants. However, in the case of wet oxidation, we need twice more oxidants to oxidize our silicon atoms. Okay, so are you with me? Let's say that if we have 100 silicon atom and I wanted to oxidize these 100 silicon atom. In that case, we need 200 H2O molecules, but on the other hand, we need just 100 O2 molecule to oxidize this 100 silicon atoms. So the required number of oxidants can be different uh, depending on the type of process. Okay. So anyway, here we have oxidants in this gas phase. Here we have ambient and oxidants are in its gas phase. However, point is the actual reaction is not occurring in this point. Okay, this is the front end of our silicon dioxide. So oxidants come to here, then it immediately becomes silicon dioxide. No, this is not a correct view. Because here we have already oxidized SiO2, there is no additional silicon atoms to be oxidized. Then where can you find silicon atoms to be oxidized? Yes, so we have silicon atoms to be oxidized existing here. Then it means that our oxidant should penetrate this silicon dioxide layer, and eventually when it meets or when they meet a silicon atom located here, then the reaction occurs. Now it becomes a silicon dioxide. So that is the kinetics of our oxidation process. So you know that the is key is the transport of our oxidant from top to bottom. After that, it should have a certain chemical reaction, and this chemical reaction rate and flux from top to bottom to be balanced to each other. Okay. So I want to say, let me just delete all ugly things here, and let me just summarize here. Diffusion of oxidants, that is corresponding to this reaction. Transport of our oxidants from top to bottom. Here bottom means that the interface between oxide layer and silicon substrate. And we must have chemical reaction at the interface. So So that is one thing. And you know, here we have one thing to be noted. And when we have this kind of reaction, volume is expanded, so 125% expanded, because we have different uh, densities of silicon dioxide and silicon. So previously, let's say that here we have a pure silicon. Then in order to convert it to silicon dioxide, actually we have to introduce O and another O into it. So therefore, we cannot confine these three atoms in the same volume, since two additional atoms were introduced, so volume should be expanded. So yeah, that is thing. So usually when you have this one, then there is some ratio like this. This part is consumed and another part is consumed here. So anyway, we have volume expansion. So this is just taken from other books about the semiconductor process. So let me just briefly discuss about the general properties of oxidation. So why we are talking about dry and wet etching? So if one is much better than the other, then we can just exclusively select one process. However, um, dry oxidation and wet oxidation has pros and cons. For example, in the case of dry etching, unfortunately, oxidation rate is low compared with wet oxidation. So here, low oxidation rate, and in the case of wet, much faster than dry oxidation. However, there is another factor. Wow, we can make it quite fast. However, however, the material characteristics is not as good as that of dry oxidation. So if you wanted to have good quality, then you have to select dry. And if you wanted to make a thick one whose quality is not that important, then wet oxidation would be a selection of your method. Okay, so there is a two thing. And as you can see here, temperature dependency is quite severe. But oxidation rate increases significantly with furnace temperature. That is quite easy. If you introduce a higher temperature, then your oxidants can diffuse quite easily, and also chemical reaction can be enhanced. And also pressure, oxidation rate increased, also the pressure in the furnace. Okay, and finally there is something like a crystal orientation dependence. So oxide growth really depends on surfaces. So is it because the available number of silicon atoms are different between different surfaces? So anyway, in reality, there are many different parameters which affects uh, the real thickness and quality of oxidized layer. So our goal is not uh, talking about every detail in this experimental result, but we are now more interested with the model to describe its oxide growth. So I think that to all of you living in 2023, so oxidation seems to be quite natural and just a granted one. However, let's come back to the time scale, like 1960s. At that time, it was really infant stage of our semiconductor fabrication. At that time, the quality control or thickness control of our oxide layer was quite important. So at the time, people wanted to know how can we control the, the thickness and quality of our silicon dioxide layer. So there were many attempts, and most successful one is so-called Thiel global model. And this is one guy and another guy. Maybe you have heard about his name already. No? Okay, so he is a founder of Intel. Okay, so anyway, in this paper, in this seminal paper, they say that there are three different mechanisms. So one, two, three. I have already discussed about diffusion and reaction, and another one is transportation from the bulk of oxidizing gate to the outer surface of oxide. So it means that. So let me just come back. So here I have talked about transport from here to there inside the oxide layer and chemical reaction. However, also there is some source of our oxidants, and it should also transport it from this source of oxidants to the ambient. So there are three different procedures: one and two and three. Yes, so they are important mechanisms. So, and they say that since we have three different procedures on something like this, so let's say that you are doing some play. Here, one guy, and another guy, and finally another guy. Yes, we are a team of three persons, and there is a certain box in. Oh, this is a box. And here you have a ball. You have actually tons of balls, so many balls. And the rule of this play is, in this case, you just throw it to the second guy. Then he or she can catch it. In the next time, he or she should kick it. And finally, this guy should touch with his or her head. So let's say that after that, this ball should be entered into a box. So let's say this is a simple game, and what we wanted to do is this just to increase the number of balls inside a box. So all of them are playing quite eagerly, because that is related with their, how can I say, their dinner, for example, that they are playing quite eagerly. And we are watching it. Oh, they are playing. Oh, so interesting, so funny. Then what will happen? This guy will send a certain amount of, certain number of balls, and this guy will kick. And another one. So how then we can count something like this. How many balls are transferred from this guy to the next guy per minute? How many? And also we can count how many balls are transferred from this second guy to the third one. Also, we can count the number of balls. Finally, also we can think about how many balls are entered into a box. So if they are playing quite well, they are well educated and well exercised, then what will happen? The number of balls in this 1 to 2, and from 2 to 3 and 3 to 4 will be the same. So are you with me? So let's say that this f and this f and this f should be the same. Let's say that unfortunately, let's say that unfortunately this guy is not that much, how can I say, experienced. Then what will happen? Okay, balls are coming. However, he or she cannot kick quite well. Then what will happen? So we have many balls are accumulated. However, those balls cannot be tossed into the third guy. So the number of balls will increase. However, in the case of an idealized case, what will happen? So the number of balls and number of balls and number of balls, these three cases will be perfectly balanced and there is no remaining balls for each guy. So that is the idealized case. So in this so-called Dilgrove model, so the authors assume that, okay, if we have three different processes, then the flux for the first, second, and third should be the same. That is the idealized case. So the derivation is quite simple here. So here we have gas phase, and this gas phase is, please note that I just rotated our drawing from vertical way to the horizontal way, so means that the gas phase was drawn on top here. This is gas phase and this is oxide phase and silicon phase, and we are just drawing this line along vertical direction. And now let's try to the concentrate of our species. So that is what I want to do here. And this cut line is now drawn in this one. Now you understand this is gas and this is oxide and this is silicon, and reaction occurs at this point because oxidants propagate from their source, then go to here, the upper surface of our oxide, then this one. Here we have gas phase of oxidant, and here we have, although quite close to each other, this is already the oxidant inside our already made oxide layer, and now it propagates from here to there and eventually meet our available silicon, then chemical reaction occur. These are three different considerations here, and of course we can consider something like this. Here we have a source of our oxidant. This is the nozzle for putting our oxidant molecules. However, we assume that at least in this part here, more or less the concentration is well uniformly distributed, and we neglect this first source, first flux, and here only consider the flux from gas phase to the phase inside the oxide layer. Okay, so let me just consider these three cases: 1, 2, 3, and here we have the gas phase concentration, and this is CO is the concentration of oxidants at the top surface, not bottom surface. And if we have something like this, C star equal to CO, then their concentrations are completely balanced. So maybe there will be no phase change from gas phase to the oxide phase inside oxide. So the difference is the driving force for our flux 1. Of course, this is the unit of molecule per cubic centimeter or any kind of volume. But flux, what is the dimensionality of this flux? That will be number of our oxidants per unit area and unit time. So you know that that is the dimension of any kind of a flux quantity. So of course they have different dimensions. So we have to introduce the coefficient to relating these two seemingly different quantities. Anyway, this is the flux 1. After that, now we have to consider propagation of our oxidants inside the oxide layer. Then what is, so for example in this case, so O2 or H2O can be here, also can be here. It is quite natural that the profile is higher at the top surface and lower in bottom surface because the source is located here. So therefore, maybe since the distance is shorter and distance is longer, it is expected that we have gradient from here to there. So maybe it is not quite reasonable. For example, if we assume a profile like this, that is quite intuitive, counterintuitive. Okay, so therefore now we can think that okay, at top surface we have more oxidants and bottom we have a lower oxidants. So if we have a difference in concentration inside a certain range, then we can expect that there will be certain behavior called diffusion. So our oxidants will diffuse into this substrate, silicon substrate layer. And of course, that is given by this one. So D, this is diffusivity, and round C over round X. However, please note that if we just calculate round C over round X, then maybe that is a negative quantity because we have a down, how can I say, downhill for our concentration. But anyway, please understand this quantity as just absolute sense. And in this case, we take CO minus CS. CS is once again just concentration of oxidants, however, at the silicon oxide interface. Okay, so this is nothing related with the density of silicon atoms. Still, this is the density or concentration of our oxidants. However, the location is different. This is of location at the concentration at oxide gas interface, and this is the concentration at silicon oxide interface. Okay, so are you all with me? So now we can write down in this way. This is diffusion. And finally, we have this quantity. So this is the coefficient for chemical reaction, and here we have a concentration of oxidants at silicon oxide interface. Of course, since our reaction is like a silicon and to silicon dioxide, so of course we have to have a certain term related with silicon. However, we assume that there are tons of silicon atoms already available in this silicon substrate, and that's true. There are a bunch of silicon atoms already in silicon substrate, and number of silicon atoms cannot be a limiting factor of this flux. This chemical reaction is solely determined by just number of oxidants in or oxidants at the interface. So that's the reason why we have just a coefficient for oxidants. Anyway, so these fluxes can be defined quite well defined. However, we must have certain assumption. F1, F2, F3. These F's, these fluxes just to describe each reaction. However, we say that they are all identical to each other. It means that if we come back to my previous drawing, so it means that in this case everything is so ideal, and number of atoms sent from 1 to 2 and 2 to 3 and 3 to 4 are perfectly balanced, and actually there is no accumulation of balls at a certain point. So following the same philosophy, we will just say that okay, all of these quantities, these fluxes describing different processes have the same value f. Then yes, after, so let's say that this is f, and this is also f, and this is also f. In this case, what happens? This F contains kind of a C star and CO. Also, it has CO, CS, and CS. There are many things. However, fortunately, we can eliminate this one. Also, eliminate CS, then we can express this f in this way. So that is not that difficult, so you can do it. So this is your, not your homework, but please do your exercise when you come back to your position or your office. Okay, so under this assumption, now we believe that here, now let me draw once again. Here we have a silicon substrate, and this is already oxided layer, and now we have a certain flux F for chemical reaction. So number of oxidants are provided to chemical reaction. Then our ultimate goal is to describe the time-dependent change of our oxide layer. How deep is it when time has elapsed? For example, if we make a certain oxidation procedure after for 30 minutes or 1 hour, 2 hours, how deep is our oxide layer? That is our ultimate interest. So that's the reason why we wanted to talking about change of x sub o. Then we wanted to calculate this one. XO can be a function of time. So what is it? If we can build a differential equation for this ratio dxo over dt, then that will give us some description about or time evolution of our oxide thickness. That is the point. So then, how can you calculate this one? Think about this one. Let's say case of dry oxidation. So we provide certain O2 atoms. How many atoms per second per square centimeter? So let's say that we have just 100 atoms per unit area and unit second. Then it means that our how can I say our silicon 100 silicon will be converted into silicon dioxide layer. Then what happens if we have, let's say that, so changing from silicon to silicon dioxide layer, let's say that we have a certain um, change of XO. Okay. Now our oxide layer was thicker than previous case. Then how can we calculate this one? This is flux. So who calculated this flux? You can calculate this flux using this one. If you understand the concentration of your oxidant at gas phase, this is gas phase concentration, then you can calculate F. Please note that this gas phase density can be controllable parameter. How can you control this gas phase concentration? You just supply your oxidant into your furnace, so you can control the gas phase concentration. And here you have different values like diffusivity or H and Ks, K sub S, and H or K sub S are related with the chemical reactions. So they are material parameters. So they are given. And also diffusivity inside oxide, that is also material parameters. So they are all material parameters and only depends on current value of our oxide layer. Okay, so simply speaking, what I wanted to say is that how can you calculate F? Okay, you can calculate because you know C star and you know H and you know K sub S and you don't know actually X sub O oxide thickness, but that is actually our unknown variable. We want to know this X sub O. So without this, except for this X sub O, all other quantities are well known. At least it is assumed that we know those quantities. So now, okay. So now this is like this. Here we have the forms like this. Please have a look at this one. This one says that n times dxo dt equal to f. So are you with me? So it means that if we just send it to here dt, then what we can have is with a short time scale with dt, the flux is multiplied. Then it is related with flux times dt. So if we will multiply some time scale constant, then we will have some values per area value. that is also balanced by what? This is N is actually the volume density of our oxidants. In the case of a dry etching, it's like this, and this is the quantity per unit volume, and dxo, incremental change of your thickness, is also centimeter scale. So when multiply them, then you can find that this is corresponding to per unit area quantity. So please think about this equation. So of course, this is related with, this number is related with dry etching, and as I told you before, in the case of wet etching, we need twice more oxidants. So in the case of dry etching, actually C is related with the density concentration of O2. However, in the case of wet, sorry, not wet etching. So this is my typo. Sorry, wet, not wet etching, wet oxidation. Sorry about that. And this is wet oxidation. And this wet oxidation case, C is related with the density of H2O. So we need twice more, C to have the same thickness increase. So that's the reason why we have a different M values here. So anyway, so now we have this kind of description, and as you know, F was previously written as this form. Now you can have this form. Then let's think about this one. In this differential equation, what is the unknown? The unknown is XO, and we wanted to the time evolution of XO, and here we have source term, and this source term has certain things like this. This is constant. When you fix the type of your oxidation, you have the fixed number. And this is controllable number. You can control the density of your oxidants in the gas phase. And here, case of S, H, they are material parameters, and you know it. And D is also material parameter. At least you know. And here we have once again unknown parameter. So there is a unknown variables and all known coefficient. So now you have just one first order uh, differential equation. So they can be combined into in this way. We have introduced capital A and capital B to simplify all of these seemingly complicated coefficients without ordered by their complicated notations. And then what are A and B? So are you with me? How can you calculate A and B? So in this case, in order to get A and B, you can simply multiply 2 times D, 2 times D. This is a unity to upper part and lower part. Then you will have 2 times XO plus H over 2D over H and 2D over K sub S, and you have 2D times C star divided by N. So then let me ask you once again, what is A and what is B? Yes, this is corresponding to your B, and this is corresponding to your A. Anyway, they are all known quantity. At least experimentally we can determine these A and B parameters. So now let's go to this one. After that, yes, you can just multiply it to here and integrate the time variable from 0 to t. So after integration, you can find this expression for your XO. Here you have XO and your XO, and A are known and B are known, and T is time variable. So, and also here we have a constant, integration constant tau, but that tau is related with the initial thickness x sub I. So you can easily measure the initial thickness. Okay, so then now it is quite easy to solve x sub O, because this is just a parabolic equation. So this is a square term and linear term and constant of XO. So now your XO, the thickness of your oxide layer as a function of time, can be simply written as these values. Here you have A, B, tau. With this one, you can predict, at least theoretically, the thickness of your oxide layer. So, are you with me? So, if you have any question, then please let me know. So,
XI가 X 제로인 거죠?
there is no x0. So here O, this is not numeric number 0, but this is O. So O is introduced because we wanted to express the thickness of O. And here xi is actually defined as xo at time equal to 0. So the initial thickness of your oxide layer. Okay, okay, good question. So please give me any question. So when you have a question in your mind. So now think about two limiting cases. So two limiting cases means that tau becomes quite large, or sorry, not tau. Tau is just constant. T goes to infinity, or T goes to 0. In this case, if we have T goes to infinity, then this tau is now negligible compared with this T. Then what happens? In this case, also this 1 becomes also negligible. So we will have just something like this. A square 4bt. So are you with me? This is not important, and this is not important. And here we have a -1, and even that -1 is not important. So we have just a over 2. And a over 2 can be easily cancelled to each other. No, this guy's gone, this guy's gone. So eventually we will have just B T. When we have quite high value of T. So time has elapsed sufficiently, then we will have just square root behavior of our thickness increase. It means that time has elapsed quite a lot, then our oxide is not growing fast enough. Why it does not grow fast enough? It is because already we have spent quite a long time, and now our XO is large enough. Then our oxidant should propagate this thick oxide. So therefore, its growth is hampered by this thick oxide. However, in the case of a short time scale, then what happens? In this case, maybe it is dominant and it is just a second order effect. So you can just follow this approximate form. So please try this t as a small quantity, then you can just linearize it, then you can find this form. Oh, in this compared with this square root dependence, in this case we have just linear dependence. Oh, it means that if we spend twice more time or 3 times longer time, then our oxide thickness becomes twice, 3 times. It is quite much expected. So, simply speaking, this Deal-Grove model correctly described that initial fast oxidation rate and later saturated oxidation. Okay, so here you can say that there are two Deal-Grove parameters, B or A, and whatever B or A or B and B over A, something like that. Anyway, you can describe it. Of course, at a specific case, you have to have an initial time constant tau. So there is one example taken from certain experimental result, and let's think about some 1000 Celsius dry oxidation. In this case, from the experiment, we have found that these two Deal-Grove parameters are given in this way. So, B has the physical dimension of diffusivity because, what was it? So, maybe you remember, B was given as, yes, this one, that was B, and C star over N, this is just a unitless quantity, and B is just different values or multiplied values of our diffusivity D. And A is simply a thickness, that is a length scale. So that's the reason why here we have dimension of a certain squared length over time, and here we have just length over time because it has a length scale quantity. And in this specific example, time constant is given by this number. It means that we assume that our initial thickness is 23 nanometer. So now you have the expression, something like this. Please use this expression to draw your XO as a function of time. Then when you do it correctly, then you will find this one. From initial time to 1 hour, we will have thickness difference from 23 nanometer to something like about 70 nanometer. And if you have something like this, oh, I wanted to have 40 nanometer thick oxide layer, then what happens? So that will be your values for oxidation time. Of course, we cannot believe this number exactly. So this should be used as just a first guess for reasonable time scale, and you must introduce some splitted experimental conditions, and with those numbers, then you will find the optimal one for your facility. So are you all with me? So this is one thing, and this is quite much related with your homework. So your homework problem 1 is just to draw your own graph for the previous example. So now you have the equation. The thing you have to do is just to draw it within time scale of 1 hour. Okay, so I think that all of you can do it. But for example, if you are using Python, then you have to install some libraries to draw something. If you have a MATLAB, unfortunately you have a built-in functionality to it. And if you are working with C or C++, then C++, then please write down a list of your thicknesses, then import it in a different drawing tools and draw your own graph. The purpose of this problem one is quite simple. You must be able to draw a graph. So please attach your code, and as I told you before, please make your report. I will not learn each of your code. So please provide your report, okay, and discussion.
주가 잘못된 것 같습니다. 주가 저 5년.
So sorry about that. So sorry about that. So let me just okay. Thank you for your good question. So obviously your September 4th, just before our next Monday session start. Okay, so sorry about that. I have to change it. Okay, good question. And any other question about homework problem one, or any question on our lecture material? So I think that that's all for our spring semester. However, we are now in fall semester, so I have introduced a little bit more. So now you understand, given coefficient or given parameters a and b and tau, I can expect the time evolution of our oxide layer. And in order to solve this one, you introduce this differential equation. So maybe you remember it. Then multiplying this a plus 2b into here and integrate it from 0 to t over dt. That gave you your current expressions. So of course, this differential equation is analytically solvable. But point is, unfortunately, your problems at hand in this semester, almost all of them are not analytically solvable. So therefore, you have to develop a skill to solve a differential equation with certain numeric sense. Okay, so that's the reason why instead of solving it with available analytic way, but let's just solve it with a computer. Let us solve the above equation numerically. Then later, let's try to make a comparison between your exact analytic solution and your approximate numerical solution. Okay, so let's consider two time instances, t sub k and t sub k plus 1. For example, you can select it like this. T sub k can be just k times, integer k times of unit time step delta t. And tk plus 1 can be regarded as just k plus 1 times time distance delta t. So if you take this delta t as a small number, then you can say that, okay, t sub k and t sub k plus 1 are so close, therefore difference can be used to describe this derivative. Although we have to have here, we must have limit in case of t sub k plus 1 is approaching to t sub k. If we take delta t as quite a small value, then maybe this limiting operation can be omitted. Okay, so therefore, please understand, already we have an approximation. This is not exactly equal in a rigorous sense. However, we believe that it is good enough to introduce this approximate expression for our purpose. Okay, so are you with me? So it is an approximation. So it, please use this approximation at your own risk. I mean that you can select these delta t values quite large in order to increase the speed of your simulation. If you want to get your result quite fast, then the best way is, why don't you just select as a 1 hour? Starting from 0 hour, just to jump into 1 hour. Then you will have just one step. But do you expect that that is a small enough number? Certainly not. Then your result, your simulation result, your calculation result will be obviously wrong. So, therefore, you must have a certain sense about what is enough for our discretization. So, instead of that, now let's think about a different extreme. Now, you say, 1 nanosecond is used as your delta t. Then what will happen? Of course, this is quite good for the approximation. In this case, you can say that it's close to the equality, not no longer approximation. However, then how long it will take for you get the solution of this 1 hour oxidation? It will take forever because you need 1 billion operation for this calculation. So please take reasonable value for delta t. Then you will get certain balance between quality of your calculation and efficiency of your calculation. But anyway, if we adopt this approximation, then this derivative can be approximated as this difference between here values of your oxide thickness and time difference. Then please use this approximated form to evaluate this round dx over dt. Then you will find, I just introduce this expression, and we assume that already we know thickness at t sub k, and we assume that we know xo at t sub k. This is known, this is understood, and we assume that this is unknown. Then, and you know, this this all of these quantities are given parameters. Therefore, now we can rephrase this equation like this. So oxide thickness in the next time step, T sub k plus 1, can be calculated from the present thickness, the current thickness, and incremental change. And that incremental change is once again solely dependent on our current oxide thickness. So starting from T sub 0, T sub 0, you have 23 nanometer, and T1, using this expression, you can calculate the T XO at T1. Then move to T2. Then once again, using this expression, you can calculate. Repeat this time marching until you arrive at, in our example, 1 hour. Then you will get the time evolution of your thickness. Of course, you have to save or store all of the intermediate values to draw your oxide thickness. So we have a second problem. This is a real problem. Repeat the problem 1. However, in this case, do not use our analytic solution. That is perfect, and that is our reference. Instead, please try to calculate your oxide thickness approximately and numerically with this expression. As I told you before, the accuracy and efficiency of this calculation solely dependent on this delta t. If you take this delta t is high value, then you will have fast simulation and low quality result. And if you have a sufficiently small value for your delta t, then you will get longer simulation time but almost perfect agreement with your analytic solution. So please try various values for your delta t and compare your result obtained from analytic solution and numerical solution. Then you will find some feelings about what is the limitation of your numerical approach and what is the advantage of your numerical approach. And also please attach your code. So that's it for today's lecture. And if you have any question on homework problem or lecture material, then please let me know. Do you have any question? No? Okay, then once again, due date is not today, but due is changed. Also, I had 2 typos, and I will fix those typos and upload it once again. And thank you for your attention, and let's see you on next Monday.